Good morning, everybody. Can you guys hear me well?
Yes.
That's very nice. I'm just gonna put like some headphones on just to make sure that this is clear. So for today, we're not gonna have a quiz. It's just gonna be a first detection lecture, and then we will. How about now? Can you guys hear me well?
Yes.
Okay, but it's not working. Let me fix this. Recording. Okay. Works well. Now I cannot hear you guys.
We can hear you.
Yeah, my speakers are not working. That's sad. Okay. Let's throw this. I can just use this one. So as I said, as I was saying, for today's lecture, we're going to have a small revision on object detection. And then we will speak about our lecture on object segmentation or image segmentation. Well, today we're not going to have a quiz, mainly because some of you guys sent me a message saying that that the lab about YOLO v4 was a bit not clear. So we're going to have a small recap of YOLO v4 lab during like the final part of today's lecture. Object detection. Nice. So yeah, as we said last time in the object detection lecture, we spoke about the object detection in general, and then we just proposed like some simple algorithm to do that. And then we spoke about the fast and faster RCNN, which are part of the RCNN family, and finished it with a small revision about YOLO. So as we said, in object detection, the main difference between image classification is that you no longer just classify one object inside the image, but you're classifying everything inside the image. And you don't just classify it, but you specify the location of that object inside the image. We saw that it has so many applications, so far parking law monitoring, and we spoke about facial detection and aggregation in a following lecture. So our simple model was just a sliding 2D CNN model. And as we saw, this model suffers from a lot of problems, such as speed, such as accuracy, and many others. We solved the problem of speed of this model, of this 2D search model, if you remember, during the RPN part of the lecture, where we no longer search inside the image, but we are searching inside of a latent space, right? So we're searching inside of the, we're no longer searching on the image, we're searching inside of the feature map, right? So this allowed us to drastically reduce the amount of passes through the convolutional layer, meaning we reduce the time of execution of such a model. We also saw that there is another algorithm that is quite frequently used in object detection, which is selective search. Selective search algorithm is not a neural network-based algorithm, but it's simple pixel combination, like clustering technique that proposes interesting regions inside the image. Another concept that we have covered was the intersection over union, which is the equivalent of accuracy in classification for object detection. And this concept allows us to basically measure the similarity between two bounding boxes. So these two bounding boxes can be two predictions, or they can be a prediction and a real bounding box. So here we can see that it is the intersection divided by the union. The intersection, the higher it is, the better for the similarity, and the lower the union is, the better for the similarity. We know that the intersection can never be higher than the union, meaning this value is always between 0 and 1 because they're both positive, and this one is maxed by this one. We also spoke about non-maximum suppression as a technique to fix the problem of overlapping predictions. And it simply does, what it simply does is just takes the maximum prediction inside a region, and it does that by following this simple algorithm, which is starting from all the predictions, we take the highest confidence score, and we remove anything that has a high intersection over union with that high confidence object. And then we repeat this iteration again and again until we just go through the whole predictions list. Just so I would remind you guys, this is not like a recap to repeat the lecture. This is just like a preparation for the object or image segmentation lecture. So I just wanted to make sure that these architectures are very well understood, as the next lecture will be just building on top of this, right? The first architecture that we studied that is really the object detection model is simply the RCNN model. The RCNN model is a very basic algorithm, and it starts with using or extracting region proposals or regions of interest using the selective search algorithm, and then every single region is sent through the CNN for classification and bounding box regression. There are so many problems with this algorithm since it's a very basic algorithm, and some of them are the training time and the inference time, which are too high. And the most important one is that selective search is not dataset specific, meaning there's no learning in the extraction of region proposals, and that's never a good thing, right? The second algorithm is the fast RCNN. The fast RCNN still uses the selective search algorithm, so still its results are never good, but it has improved over RCNN by using a very simple trick, which is we no longer send every region through the CNN. Simply, we send the image once through the CNN, and then every single region of interest that the algorithm has given us, we just find its mapping in the convolutional feature map. We do not compute its convolutional feature map again. We just find it or find its corresponding location inside the convolutional feature map that we calculated only once. Finding it is a very simple algorithm, as you can see. It's just mapping the basic coordinates from an image to the feature map. This allowed the model to be much faster. So this is a much faster model, as we can see in here, during training and during inference. But we can clearly see that the main problem or the main time-consuming thing inside this algorithm is the selective search algorithm. So if we want to move on forward and improve this algorithm, we must ditch the selective search algorithm. And this is why we have the faster RCNN architecture. Simply, it is fast RCNN, as we have studied it before, coupled with region proposal network. So region proposal networks are very basic architectures, and this is exactly what we have, let's say, predicted, or we have proposed in the start of our lecture, right? So we propose to be sliding a classifier throughout the image and just predicting is there an object or not over that slice of the over that window that we were working on. So here we can see that RPN, unlike our proposed algorithm, does not slide through the original image, but to simplify the process, they first send the image through a backbone, a CNN backbone. In this case, it's VHG, but in future architectures, they're using, as we have seen, what are they called? Pyramid networks. I forgot the name. Yeah, but as we know, they just extract for us a simple feature map, and then we slide our classifier on top of that feature map. So sliding on the feature map is pretty easy because the feature map's dimensions are much smaller than those of the original image. So this process is much smaller, and it's it's not an iterative process, but it's more like a parallelizable process, right? So it doesn't take a lot of time. So just to go a bit into more detail about the RPM. So here we can see that, for example, at this point, if we are looking for objects in this area, and we put a classifier on top of this region, it maps through the image as these different locations, right? So we're not just going to slide one classifier, we're going to slide several of them. And these classifiers are going to be called anchors. So usually in the original paper, they were sliding 9 different anchors. So as we saw that there are 3 combinations of each. So there's the rectangular one, there's the horizontal, there's the vertical one. And of course, there are 3 different sizes. There's small, medium, and large. Here we can see that we're sliding this small window of different anchor boxes on the feature map, and we send it later on for classification. So 2 times 9 scores, and for regression, 4 times 9 coordinates. So just to recap, the faster RCNN is a very simple architecture that combines fast RCNN with another architecture called RPN, which are region proposal networks that replace the selective search algorithm. So this is a quick recap for the RCNN family. And then later on, we spoke about the YOLO family, and YOLO is a very simple model. So YOLO is just a set of convolutional layers, like following each other. And what we have in the end is simply a convolutional feature map that we treat in a special manner, right? So in this case, only thing we have is just a couple of CNN features or a couple of convolutional layers that will lead us to a convolutional feature map that we treat in a special manner to get the outputs. So here we can see that there are like 3 layers of processing, right? So there's the first one. This one works with the largest objects. This one works with a bit of medium objects. As you can see, the size of the image here is a bit bigger. And here we work with the smallest of objects because they are still visible, because they are only visible here. Here, only thing that can remain visible is the larger objects. And we're able to do this processing only because we apply some upsampling here. And of course, we apply some residual blocks between the previous convolutional feature maps and the future convolutional feature maps to process basically for medium and smaller objects so that we don't lose any of the information contained in the image. At each step, one of these 3 steps, we're going to do the following. So every single one of these pixels will contain 3 boxes. 3 boxes correspond to 3 anchors. So these 3 boxes correspond to 3 anchors that we are sliding on every single feature map. And each one of these boxes contain the following. Simply, they contain the coordinates of the objects, or the improved coordinates of the objects, the objectness score, and of course, the class. So the number of filters in the last convolutional layer, or the number of channels in the final convolutional feature map, are the following. Number of classes plus 5 times 3. So remember this formula, as we have seen in the lab. It's very important. So this is it about the recap of object detection. Does anybody have any questions about this one, or should we go directly to the image segmentation lecture?
I have a question. Could you please
Yes, go ahead.
explain once again how ROI works? ROI pooling.
ROI pooling, that's a very good question. Let me just pull it up like this. present. So we proposed ROI pooling in this lecture, right? So here, simply what it does is, okay, let's go back. So here we said we're going to send different convolutional feature maps through a set of fully connected layers. This causes us one small problem, right? So usually whenever we send a convolutional feature map, we just flatten it. So we convert it like this into a vector, one-dimensional vector, and then we send it through the fully connected neural network. So there is no problem in this. But if we have different sizes of convolutional feature maps, when we convert them into a one-dimensional vector, or when we flatten them, they will have different sizes. Different sizes of vectors can never go into the same fully connected neural network. So this is the main problem. How can we solve this problem? By using ROI pooling. ROI pooling is a very simple trick. You take this feature map and you take this feature map and you convert each one of them into the same size. How does it do that? Simply by taking the maximum over a region. Let's do a small example. Let's say that I configured my ROI pooling layer to convert everything into this 2x2 square. So any shape that I give it must be converted into a 2x2 square. Let's give it like a shape like this one. So this is a 5x3 square. What you do is you divide the original image into regions, right? So you're going to divide the original image into regions. This is region number 1. So let's say it's like this. This is region number 2. This is 1, and this is 2. This is 3, and this is 4. You see? Then for region number 1, you take the maximum over region number 1. Region number 2, you take the maximum of region number 2. Region number 3, you take the maximum of region number 3. Region number 4, you take the maximum over region number 4. And that's it. Does that answer the question?
Yes, thank you.
That's it. That's great. Now let's go to the image segmentation task. So the image segmentation lecture should be a pretty easy one, as long as you guys remember a little bit about the task of, what is it called? Autoencoders. So this lecture is going to be a simple one. We're going to speak about variational autoencoders. We're going to speak about segmentation in general. And then, of course, we're going to speak about different architectures for segmentation, which are SegNet, UNet, and the mask RCNN architecture. So previously, before what are they called? Before deep learning, what we were doing is taking an image, extracting features from that image, and then sending them for classification. Can somebody tell me what are the techniques that human beings used for feature extraction before deep learning?
Like we apply different filters.
Yes, nice. Histogram-oriented gradients.
Yes.
All of these concepts that we have seen before are handwritten examples of feature extraction made by human beings and applied to images so that we can extract features from these images and perform classification. Now for deep learning, you give it the image as it is, and it is going to learn the weights of these feature extractors from the data, right? So you no longer have a specific set of filters which are like completely, how do we say this, fixed, so do not change. Now you have a set of filters that you just define the size of the filters, and the weights are going to be learned from the data. This allows for much greater accuracy, of course. Now, autoencoders, now I hope some of you guys are already familiar with autoencoders. So from my side, what I'm going to do is simply explain them in the most easy way possible without going into a lot of mathematics. So for those who understand autoencoders and especially variational autoencoders, so you are familiar with the amount of mathematics behind. So for those who do not understand the mathematics, this course was not going to cover them, but hopefully the advanced computer vision course, if you go there, we're going to cover it in more depth. So simply, an autoencoder is a feed-forward neural network that is trained to attempt to learn a structure in the data. Simply, what we do is we take an image, say this is a 4, and we try to learn some sort of representation of that image, or try to learn some sort of a code of that image that is much more dense, right? So for example, here we have 4, which is like 32 by 32. We try to learn the information inside this 32 by 32 image and summarize it in, let's say, a 3 by 2 or a 4 by 2 example here, right? So we're going to summarize this whole image in only 8 features or 8 values. This is the goal of autoencoders, and it does that by trying to learn this feature space or latent space or encoded space by encoding the image into a lower dimensional space. And then from these values, we're going to come back and reconstruct the original image. So if we were able, or if we managed to actually reconstruct this image only from this information, so we give a neural network only these values and we ask it to reconstruct the original image, this means that these values contain all the information needed for the reconstruction, meaning these 8 values contain all the information that can be extracted from the original image. So first step is to project the input into an encoded space. Second step is to reconstruct it or decode it back into the original space. So here, for example, we take an image of this smiling person and we extract, let's say, some features. Of course, the features that are going to be extracted are not going to be humanly interpretable, but just for the sake of understanding, we will consider these are the features that the neural network is extracting. So this is the latent attributes or the latent space that autoencoder is generating. So here, for example, we have smile set to 0.99 because he's smiling. We have skin tone, 0.85. We have gender, minus 0.73. We have a beard. We have glasses, close to 0 because he does not have any. We have hair color, 0.86, which kind of represents black for the model. And then what the decoder is going to do is just look at this information and try to draw a new face that corresponds to these features. There are 2 main components in autoencoders. We have already seen them, but to go into more depth, we have the encoder part, which is sometimes the most important part, and we have the decoder part. For different applications, it is the most important part. Most cases, especially in research, you're not going to use the encoder and the decoder. You're going to be interested in just one of these 2, right? So either you're going to train a very good encoder or you want to train a very good decoder. But it's rarely the case where you use both of them during the same time, right? But the first one is the encoder. As we said, it just creates a hidden layer containing code to describe the input. And the second layer is just creates a reconstruction of the input from the hidden layer. So let's just try to see what are the use cases of each one. Imagine that you are building CNN and you don't have enough data, right? So you don't have enough data. What you're going to do is you're going to do fine-tuning, right? But sadly, you don't have enough data even for fine-tuning. The simple thing to do is build, for example, an autoencoder on the data. This autoencoder or this encoder is going to be forced to learn so many things about the data, extract so many good features about the data. Later on, what you do, you remove this decoder completely and you replace it with a fully connected neural network that does the classification. So now you have an encoder that really knows the data. So you are extracting very rich features from the data, and then you just send it for classification through a fully connected neural network, and this will give you much better results than just normal fine-tuning. So remember this trick. It's pretty useful for training image classifiers when you do not have enough data. A very good application of these concepts is also something called domain adaptation. So depending on where you advanced with Professor Khan, usually he likes to finish with like a small lab or small course about domain adaptation. Domain adaptation is a very good application of adversarial learning and, of course, autoencoders. So here we can see a small paper that's working with both adversarial learning and autoencoders. So I don't think we had a lecture about adversarial learning in this course, did we?
We have a GANs.
Yeah, we had GANs, right? So that's nice. So you understand what adversarial learning is. So nice. So here what we're doing is simply, we take an image of this dog, for example. So you can see this is an artistic representation of the dog. And we send it through the encoder. We regenerate it through, or redecode it through the decoder. And now the training is pretty simple. The decoder is trying to generate the image, whereas the encoder is going in the opposite direction. It's going in the adversarial direction of the decoding. So the encoder is trying to not generate the image back, right? He's trying to filter out any information that can be useful for the decoder. So he's trying to basically remove all this information that is extracted about the original image. He's trying to remove all the style of the image. He's trying to remove all the colors, what are the different colors used, all of these concepts, he's removing them from the latent space. Why? Because they are useful for the regeneration. Simply, this allows it to basically extract features which are very bad, right? But at the same time, we are training a classifier or a fully connected neural network to do the classification. So this encoder is being forced to learn two things. It's being forced to learn something good for classification, and at the same time, bad for reconstruction. So what it ends up learning is a very good classification space that does not contain any noise or any information about the style of the image. This allows the classifier and the encoder to be more generalizable or more robust to changes. So this encoder plus classifier are now more resilient to changes in the data. So it can work with images like pictures like this one, artistic paintings, photos, all of that, it can work with it. And this is just done using a simple combination of, as we've seen, autoencoders and adversarial learning, right? So we're not using adversarial learning in this case to generate new images. We're using adversarial learning in this case to force the encoder to go in the opposite direction of the decoder. So unlike what we have seen in autoencoders, this is an application where we want to go, this is going in the opposite of this one, right? All the, so anything you guys want to do, it's possible, right? Another type of autoencoders or another application of autoencoders, let me just make this a bit smaller. Yeah, much better. So another application of autoencoders is called the reconstruction of corrupted input. What it simply does is called the denoising autoencoders, and simply you give it a noisy input and you ask it to reconstruct a denoised version of that input. Sadly, this in theory works well, but in practice does not give very good results. It's much better to replace this architecture with something that is based off of GANs, right? So GANs would be able to do this generation in a much clearer way, but still, this is an application, and this was something that was being done very quite recently, and it gave good results in these controlled applications. I'm just going to check if Professor Khan is joining. No. Yes, so as we said, we give the input image in a noisy format, and then we try to decode it in a denoised format. Of course, you might not have these, what are they called? Couples, right? You don't have this noisy image, not noisy image couples. So what you simply do is you first give it the original image like this, very clean, and then you apply some noise on that image, and that's going to be the noisy input that will be sent for the encoder, and the decoder will be asked to reconstruct not the noisy input, but the clean version of it. With enough data and with enough training time, this will give you, this will be a denoising autoencoder, something that will take noisy images and give you something a bit clearer. So there are different types of autoencoders. There are undercomplete, overcomplete, there are sparse autoencoder, and there are denoising autoencoders that we spoke about. The undercomplete autoencoders are the most common one, where the latent space size is smaller than the input size. So basically, we take an image, very high dimensional image, send it through an autoencoder, and we learn latent space that is smaller than the original space. Then we send that one through the decoder. So this one is smaller than this one. Overcomplete is basically the opposite. So we take this. Now the latent space is much bigger than the original image. But the only difference is, in this case, we will apply some sort of constraint on the content of this latent space, right? So in this case, the latent space is much bigger than the original image, meaning we can easily learn some sort of a mapping, or like the same, this pixel just comes here, this pixel just comes here, this pixel just comes here, and we're doing no learning, we're just copying the image from here to here. There's no learning in this case. Where we are forcing it to go to a lower dimension, we are making the information much dense. But in this case, when we are forcing it to go to a larger dimension, there's no learning happening here. We're just copying the pixels from here to here. And to do some learning, we usually apply some sort of, what are they called? Constraints on top of this image that will help us basically make use of these contents. Some of the constraints that we can apply is sparsity, meaning we say that the majority of these values must be set to 0. So the majority of these values should be canceled. And this gives you the sparse autoencoder. There are other types of constraints that you can apply. Any type of constraint that you can think of basically is applicable. Now the final part of autoencoders is called the variational autoencoder. And this one is a bit more interesting, right? So it gives better results for image decoding or even image generation. And it does give better results in learning more interesting feature spaces. The only big difference in this case is we take an encoder, we take an image, we encode it, and then we take the latent space from here and decode it. The main difference is we no longer have one latent space, but we have a latent space distribution. Let's go to the next slides and see what's happening here. For example, in this case, instead of saying that the smile value of this boy is like -5, or he's very sad, we say that he has a distribution of smile very close to -5. So this is the mean. And we give it some sort of a standard deviation, right? Same thing here for the Mona Lisa. Someone would say it's like 0 smile, she's not smiling. But someone would say, well, we don't know, right? So it's like a very large distribution. She could be smiling or she could be not smiling at all, but it's a distribution like this one. Same thing for this girl. We can clearly see she is smiling, but instead of saying it's smiling at a certain value, we give a distribution of different values that can be used to represent this image. So this gives it more flexibility in the learning part, and learns a more smooth, latent space. So here we can see, for example, the same image from before. We no longer have a specific value for each one of these latent attributes. We have a specific distribution that we can sample from. So later on, what we simply do is we can take this distribution and sample from it as many times as we want, and we build our decoder. This allows us to basically, from a smaller amount of data, we're going to do a lot more work. So just like it's the same image, we're going to send it through the architecture multiple times. And at each time, we're going to have different training, right? We're going to have a bit more information added to it because we're not using the same values anymore. We're using still some different values, allowing for better training. So this is the power of variational autoencoders. Sorry. So as you can see here, the variational autoencoders, they do give some very good results, but they're still not the state of the art. The state of the art is GANs. So at this time, I'm going to stop and ask you guys to give some questions. Do you guys have any questions about the content of the lecture so far? No questions about autoencoders in general? Okay, nice. So let's continue then. The second part of this lecture is going to be about image segmentation. So in image segmentation, we're trying to learn the shape of every single object inside this, or the shape of the objects inside this image. So for example, in this case, we have different people. And as you can see, we're learning the borders of these people. So this is kind of similar to object detection, as we have seen before, but we're no longer interested in just the region of the object. We're interested in the exact specific pixels of that object. There are two main image segmentation techniques or image segmentation types. There's the first one, which is the semantic segmentation, and there is the second one, which is the instance segmentation. Semantic segmentation is the most commonly researched type of segmentation, and you will have lots of architectures for this one. And of course, there is the instance segmentation, which we have already kind of seen in the previous lectures with mask RCNN, but we will go into more detail about it today. So here the main differences are the objects of the same class are represented similarly. There is no difference between a pixel belonging to this person and a pixel belonging to this person, at least in the mask that we will, in our predictions, right? But for instance segmentation, this pixel belongs clearly to person number 1, this pixel belongs clearly to pixel number 5, and this pixel belongs clearly to table number 1. So this is the main difference between semantic segmentation and instance segmentation. We can clearly, separate the pixels of the table from the pixels of the person, but we cannot separate between the pixels of person 1 and person 2. Also, we cannot count how many people are around this table from this semantic segmentation task, but we can easily do that from this instance segmentation example. So the first algorithm we will see for segmentation is the algorithm we have been speaking about during this lecture. Yep, nice. So is the algorithm that we have been speaking about during this lecture, which is the autoencoder. Autoencoders are very easy applications or very easy models that can provide us with some semantic segmentation. What you simply do is you take an image like this, you encode it into some downsampled feature map or a latent space. And then from this latent space, you're going to decode. You're not going to decode the original image. You're going to decode the mask that corresponds to this image. Of course, in order to do that, you're going to require a lot of data. So basically, you should have this image with its corresponding map like this, and then another image with its corresponding map, and then lots of images with their corresponding maps. And of course, we're going to have the autoencoder just predicting or reconstructing this mask instead of reconstructing the original image. Now, a simple question, and the answer is already on the slides, but a very simple question is, how many channels should be in the final layer? As we said, the semantic segmentation task allows us to differentiate between pixels of different classes, but not pixels of different objects of the same class. So how many channels should we have in the final image? Of course, the height and the width are fixed to the original image height and width, but the number of channels will change. In this case, we have only 3 channels, but in the output, we don't care about the images or RGB, we care about what, right? So this is the question. Can somebody tell me what is the number of channels in the output?
It should be binary, no?
Binary. Okay, very good. Can you elaborate? That's a good one. Binary means what?
Like basically we have, we are taking only the objects from the image.
Yes.
So basically we have, we're just interested in the object, and we have a background.
Nice. So either object or background, right?
Yes.
What if I tell you there is a cat in here?
Well, in this case, okay, so the cat will have like a different channel than the woman on the...
Perfect. Exactly, right. So the only difference between what you have proposed initially and this one is we no longer use this, what is it called? Is it an object or not? We're also trying to understand what type of object it is, right? So here, it's not going to be a binary classification, but a multi-class classification. And of course, majority of the pixels are going to have this 0, 0, 0, 0, 0, because majority of the pixels are going to be background. Only once, for example, let's say this is a cat, so the class cat will be turned on. If it's not a cat, for example, it's a human being, class human being will be turned on. That's it. But a great answer for this one. Thank you. So again, the output or the number of channels in the output will be n, which is the number of classes, and it will correspond to the number of, what is it called? Convolutional filters of this final layer of the decoder. The next architecture that we will see is kind of an improvement over autoencoders, or kind of just like a simple trick over convolutional autoencoders, which says we only use convolutional neural networks. Just do not how do you say? Just do not mistake FCNNs that we already know, which are fully connected neural networks, with these FCNNs, fully convolutional neural networks. They're like completely opposite. Okay, they both are FCNNs, but they're completely opposite. So try to remember, these are called fully convolutional neural networks. The others are fully connected neural networks. No mistaking these two together. But simply what it does is it takes an image, send it through what you would describe as an encoder-decoder setup. But this encoder-decoder setup contains only convolutional layers, does not contain anything else, right? So there is no fully connected layers, there are no dense layers or linear layers as you would see in like Keras or PyTorch. Only thing you will see in this model is convolutional layers. So this is like the only trick that is here. And the rest of the training is simple. You take the image, try to reconstruct the feature map, or try to reconstruct the mask of the objects, or the masks of the different classes, because we are still in a semantic segmentation task. There are different values or different versions of this model. So there is the fully connected neural network 32 stride, there is the fully connected neural network 16 stride, and there is the fully connected neural network 8 stride. This references the size of the, what is it called? The feature map used for the creation of the mask. Simply, let's do this, imagine this scenario, right? We take this image and then we make it much smaller. So if we make it much smaller like this one, if we're trying to learn the mask of the original image, so we're trying to learn the classes from this image, they would be represented in the smaller image, but the details will be missing, right? So we cannot really learn all the details of this image in this lower format or this lower space. Meaning, if we're going to reconstruct a mask from this one, the mask is going to be very messy, right? So you can see we do not have enough detail in this 32 stride feature map to really reconstruct the original image. This 32 stride means that the size of the feature map used for the prediction of the mask is 32 times smaller than the size of the original image. So basically, every 32 by 32 pixels are represented with only 1 pixel in this feature map. This makes of course, the results much worse, but it is much faster as an algorithm. There is the fully connected, or the fully convolutional neural network with 16 stride. It does give better results, so you can see it's closer to the ground truth, but it's not as good because it still loses a lot of information. And we have the fully connected fully convolutional neural network 8 stride. This one is the best one because it has the biggest feature map that is used for the prediction of the mask. But again, it is the slowest, right? So slow, not accurate. Now, depending on what your goal is, you might want to use this one or this one. So this is like, this gives you a lot of flexibility in what kind of architecture to use. The next architecture is called SegNet, right? So SegNet is again a very similar type of encoder decoder. So it's the same thing as FCNs, it's the same thing as variational autoencoders, same thing as autoencoders we have seen before. Always we take an image, learn some lower representation of that image, and from this lower representation, we're going to build back the mask or the original, this mask of the image. The main difference between what is a fully connected or fully convolutional layer neural network and SegNet is that all these different layers are being mapped to each other, right? So they're kind of, let's say, how do you say this? They're mirroring each other. So if we have seen previously a mirroring or stacked autoencoder, what you will see is that these layers, the input of this layer, it has the same size as the output of this layer. So this is the trick, basically. The trick is to maintain or to make the decoder the exact opposite of the encoder. Simply, it contains lots of convolutional layers here, as you can see. Some max pooling layers. We already know these. We have some upsampling. So as you know, to perform the deconvolutional operation, we do upsampling plus convolutions. So this gives you like the deconvolutional layer. And finally, we finish it with a softmax because we have multiple classes for every single pixel. So this is the SegNet architecture. So SegNet is sadly not very much used right now. Why? Because it's very recently been improved or very quickly have been improved by another model, which is also very similar in architecture. So as you can see, all of these models share like a lot of stuff. So all of them contain encoder, decoder, and then starting from fully convolutional layers, all of them contain only convolutional layers. There are no fully connected layers here, only convolutional layers. And then, of course, SegNet proposed that they all be kind of mirroring each other. Now, the UNet is, let's say, the final model that we will speak about today for the semantic segmentation task. And it is like an improvement over all of this history that we have been speaking about. So still, it contains encoder and decoder setup. It still contains only convolutional layers. So there are no fully connected layers or linear layers. So it's similar to FCN. Again, it's very similar to SegNet because every two are like mirroring each other. But now, on top of that, we're adding this copy operation. So the copy operation, what it simply does is it takes the feature map from this, let's call it block number 1, and it copies it or concatenates it with the feature maps going to block number -1, right? So the final block. This one is block number 2. Its convolutional feature map will be used as input for the block -2, right? The block before the last one. This allows these final layers to kind of understand, to have better understanding of the original image, right? So when you are reducing the size, you are kind of learning more rich features, but you're losing a lot of spatial features, right? You're losing a lot of spatial information from the image. By doing this copying of the feature maps, you are still preserving all this spatial information. The locations are more precise. The edges are still more precise. All of this information can be used to make better masks, right? So here we are getting more rich information that can be used for classification. Here we are using more spatial, more something that is more rich in terms of quality of the image, in terms of resemblance to the image, and in terms of the accuracy or the sharpness of the edges and all of these things. So this will help you to first, this one, the longer road, will help you to detect the classes better, understand the whole image better. But the first road, or this second, let's call it path, allows you to be able to give better, what are they called, edges, and understand the fine details in a much better way. So UNet combines both higher level information through this path, and of course, lower level information through these copy paths. Very simple architecture, and it does the job. It was proposed mainly for, what are they called? Medical images, but it's still being used till now for all types of applications, and it does give the best results for semantic segmentation. So for those of you working on projects with segmentation, you should at least check UNet. Of course, the majority of you are not going to make UNet your main model because we have still some other models coming ahead, but UNet is always very nice to use as benchmark. So just to compare your results with. The best model we're going to speak about is the mask RCNN model. And as you can guess, it is part of the it is part of the RCNN family. Basically, what it's going to do is faster RCNN plus mask prediction, right? So the faster RCNN provides you the location of every single object inside the image. And then once you have an image like this, right? So you have a rectangle with just one object inside of it. How can you predict the mask of this one?
Just simple threshold methods that we have, like after.
Yes. Can we do like something from what we have seen, like just propose some neural network for it? You already have this part, right? So you already have just an image with one class, one object, one everything. How can you predict the mask for it from the algorithms that we have seen before? Like just for the algorithms or the models that we have seen in this lecture.
Any like unit or
any of them will work, right? So basically you put here an encoder and then you put here a decoder. And the decoder will give us the mask.
Could I ask you a question about this architecture?
Did you say something? I did not hear.
Yes. I want to ask you a question about this architecture.
This one?
No, the whole mask RCNN. So first
Yes.
layer object detection, like.
Yeah, not just a little bit more time, right?
Okay.
Just so we can understand the theory of where is this located, right? So this part is semantic segmentation, right? So this is what we call a semantic segmentation. How can we convert it into an instance segmentation model? Simply by combining it with an object detector. So first we have an object detector, which is the faster RCNN architecture. And then once this faster RCNN or this object detector gives us the bounding boxes of the object, we give it through some sort of autoencoder, something like UNet, anything that you guys want that will predict the masks. So the mask RCNN architecture is just faster RCNN plus some sort of, let's say, semantic segmenter. We'll just put like a star here just because it's like not exactly that. So again, how can we make a instance segmenter? So instance segmenter equals object detector plus semantic segmenter. You see? Is the concept of instance segmentation and semantic segmentation more clear now with this formula, right? Do we have any questions about instance segmentation and semantic segmentation, the differences? Because this is something very important that it's definitely going to be in all of your quizzes and all of your final exams, right? No questions? That's nice. It's a simple concept, but it's pretty interesting. So simply what it's going to do is it will take an image. Of course, you already know that this image was sent through a region proposal network, right? And then what we did, we take these regions, send them through, or send the whole image through the CNN, and then we take the regions of interest, find their mapping inside the feature map. So this feature map is the output of some sort of backbones, let's say VGG network, or as we will see in the future labs, it's called feature pyramid network, so FPN. Very simple, it's just a convolutional neural network that will give you this feature map. And then from this feature map, we take the different regions of interest that we're interested in and send them through this ROI pooling layer or ROI aligning layer. just ROI pooling, very simple, very basic, as you guys already seen. Send it through a couple of convolutions. Send it for first bounding box and classification. So this is faster RCNN architecture. We don't care about that. Leave it be. We already know what it is, what it does. Now here, what we're going to do is we're going to send it through a couple of convolutional layers that will give us this mask for only this object, right? Of course, another one will be used to give us for this object, another one for this object, and another one for that object. And this will give us like the mask for the whole image. But at only this step, we take object by object and we predict their corresponding masks using some convolutional layers. Again, you can think of this one as a fully convolutional neural network, right? Because this is coming from CNN, and this is again a CNN. So basically the architecture that detects the masks is just some fully connected network. For fully convolutional network can be considered as a autoencoder or can be considered as, let's say, SegNet, right? So again, it works very similarly to all the semantic segmentations that we have seen before, but it is coupled with classification and bounding box regression. And of course, it's operated only on the output of the RPN or the output of the region proposal network. So first, we predict the regions of interest. From the regions of interest, we apply classification plus bounding box regression plus mask. And this gives you the mask RCNN, right? So in faster RCNN, we took the regions of interest, only did these two. Mask RCNN, we take the region of interest and perform all of these three tasks. Can you ask your question again?
No, now I don't have a question.
Nice. That's good. So that's it. This is the architecture that we were interested in. This is the model that we have seen. Now, as I've said, just in the final part, we will see the lab of what is it called? YOLO v4 lab, and we will try to cover it again. If we have enough time, we will also see a lab about mask RCNN and understand it better. Does anybody have any questions about the lecture so far? If there are no questions, then I would assume that everything was well understood. And I will ask you guys to help me build this mind map real quick, right? So this is a mind map for, let's call them object detectors / segmentation. Let's start with object detection. How many families do you know in object detection?
Three RCNN, YOLO, and SSD, single shot detector, I think.
Okay, you know just two. You don't know SSD, right? We did not study SSDs. We only studied RCNN family.
But with from article from Medium, they always classified like this, I think.
Yeah, SSD is a very good model, but sadly, it's like goodbye right now for it, right? It's just not working anymore.
That's why it was not covered. Yeah.
Yeah, exactly. So here we have the RCNN family and we have the YOLO family. Can you tell me what are the models that you know in RCNN?
Faster RCNN, faster.
Exactly. So faster RCNN. Very easy names. And for YOLO, how many versions do you know?
5.
There are 5, right? You only know 3 of them, right? You know YOLO version 3, YOLO version 4, and YOLO version 5. Of course, there is PPYOLO also, it gives very good results, but now I think it's always good to use YOLO version 4 directly. YOLO version 5 is good, but it doesn't give good results. But YOLO version 4 always gives the best results, to be honest, at least through all the cases that I've worked in and all the research papers that are being comparing the different architectures. So the YOLO v3, let's start with RCNN. So RCNN is selective search plus plus CNN, right? So every single one of the values of the selective search will go through the CNN. Fast RCNN is 1 time CNN, right? Plus ROI pooling of selective search. Faster RCNN now removes selective search completely, and in this case we will have region proposal network plus fast RCNN. The main important thing in RPNs is anchors, right? And we have 9 of these anchors. The rest, I think it will come up to you as you just look at the lecture, but it's really important to just have this small summary for everybody, for each one of you. YOLO v3 does the prediction or the object detection, 3 scales, right? So we have the first scale, which is for the large objects, we have the second scale for medium, and we have the last scale for the smallest of objects. Each one of these scales contains 3 boxes or 3 anchors, and each one of them contain the following formula: 5 plus number of classes. Right. So just remembering this will certainly give you an idea of each one of these architectures. And then we have seen YOLO v4 and YOLO v5 as just an extension of YOLO v3, adding on top of it some different bags of freebies and bags of specials. So these bags of freebies and bags of specials are just some different, let's say, hyperparameters for the training. Personally, I don't see any big contribution after YOLO v3. So all of these things are just techniques used during the training, either some pre-processing technique that will speed up or that will improve the accuracy of the model, so with different augmentations and stuff, or some a bit more complex or different, what are they called? Loss functions and training stuff. So easy stuff, right? The main thing that I want to see will come later on during the lab or the lab revision. For YOLO v4, what are the different architectures that you already know? In the lab, right? The different config files for the training. There is Tiny. This is like the one that you certainly have used during the lecture or during the lab. There's the original YOLO v4. There's CSP, scaled YOLO v4. No?
We didn't talk about it.
Okay, so we will talk about all of these during this lecture. And for YOLO v4, we have small, medium, large, and X. Previously, this medium, I really liked it a lot, gave good results. But now, honestly, always use YOLO v4, it just gives the best results. And now for the segmentation tasks, right? I think let's just take this out, put segmentation here. How many types of segmentations do you know?
Instant segmentation.
And semantic segmentation, very well.
Mhm.
Nice. For semantic segmentation, sorry, semantic and instance. For semantic segmentation, what are the different algorithms that we have seen?
Segnet. Yeah.
And last one?
Unit.
Nice. And for instance segmentation, we have seen mask RCNN. That's very nice. And as you guys know, so all of these, it's like a, let's say an improvement list. So UNet is an improvement of Segnet. Segnet is an improvement of FCN. FCN is an improvement of AE. Can somebody tell me what are the different versions of FCN that we have seen? What is this S?
Stride.
Stride.
Stride. Yeah, it's not seconds, right? Nice. So this is it. This is like a quick recap of our lecture. Now let's go through our lab and just take a look at the YOLO V4 in general. I think it was lab 11. No. Okay, let me just open mine here. Lab. That's good. Now let's go. And let's open. Very nice. So first thing I want to see is, do you guys know what Darknet is and who Alexei AB is, right? So Alexei AB is the guy who used Darknet to build the YOLO V4 implementation. And Darknet is just another framework for building neural networks, but in C, right? So we have PyTorch and TensorFlow that are written, of course, in C, but the interface is completely in Python. And we have Darknet, which is just a completely C-based framework, but it's a very simple framework. We can take a look, for example, at the code of Darknet. So we take here, for example, this is for activation functions. As you can see, they're pretty easy. Not this one. Let's see this one. No. Where are they? Activations. Yeah. So here we can see that there are the different activation functions. They're very simple. So let's. I don't know why I don't see the code for them. Activation functions. Activation kernels. Yeah. So here, for example, we have the this is LH10 activate kernel. Let's take something that we already know. So, for example, the linear activation kernel just returns X as it is. We have this logistic activation kernel, which is 1 divided by 1 plus exponent of minus X. We have this ReLU activation. Remember ReLU? So it's X times a Boolean value of X bigger than 0. So if X is bigger than 0, we return X. If it's smaller than 0, then this multiplication will give you 0. We have LU here, which is like exponential ReLU, right? We have leaky ReLU. We have tanh. There it is. Let's see. We have soft plus. We have different activation functions that we're already familiar with, right? So the goal of just showing you this code, I'm not going to ask you to write this code, but just to show you that Darknet is actually just simple C code that that is easy to read, but very difficult to write, right? So if you're gonna do some Darknet changes, you really should not, right? I hope that you guys do not. Here you will find a very detailed repo about the different architectures and lots of comparisons here. So here we see that efficient det does give a lot of good results. Oh, this is PPO, I think. This is efficient. Not sure. No, this is efficient det, right? And this is PPO, right? And the best model definitely out there is scaled YOLO V4. So the scaled YOLO V4 gives the highest, this is AP, average precision. We did not go into depth about what average precision is or mean average precision. And this is a concept that we will study in the advanced computer vision course. So for those interested in more depth or more details about how to evaluate object detection models, we will cover all of these things in the advanced computer vision course. We will have probably like half lecture about mean average precision because it's a bit of a like a difficult metric to calculate. it does require some knowledge about precision and recall and how to see them in different ways. So here we can see this is the accuracy, let's say, and this is the speed. We can clearly say that see that YOLO V4 scaled does provide the highest accuracy at the lowest speed possible. And of course, we have this model, P6 model, which provides like 3.7 times faster than this version of that efficient det, and again, same accuracy. So always, if you're going to train an object detector, always take a look at either scaled YOLO V4 or YOLO V4 as it is. And
excuse me, which data set it is?
This is the MS COCO object detection.
Currently on papers, this code shifted window transformer is top 1.
Can you repeat?
Currently on papers, the code shifted window transformer is top 1, not the YOLO.
So currently there is someone else who is providing better results than YOLO V4?
Yeah, you can see it here, shifted window transformer, it's purple. But
purple.
that picture might be outdated.
Okay, so this one, let's see if papers with code does papers with code. Object detection. Yep, here's the background. Let's take a look at it. Okay, so yeah, here they're saying that yes, that is true. I'm not really certain about these. Well, that could be true. That could be that Swain transformers is better, but for our case, we're still going to work with YOLO V4, mainly because it's much simpler and it's much, well, it's a little bit faster. And in this comparison, they're saying it's much better. So for example, for YOLO V5 and all of these architectures, for example, you don't see YOLO V5 here because mainly it's so new and people haven't really gotten used to using it yet. So we don't know if it's much better or maybe the authors just exaggerated a little bit. But YOLO V4 has been around for quite some time now, and it has proven to be very effective. But thank you so much for this comment, right? So for now, we will consider that YOLO V4 provides the best results, but keep in mind there are newer models, definitely much more complicated, but they are giving some very good results. And as we can see here, they're kind of based on some RCNN architectures. Very important things to keep in mind is the following. Let me find this here. Pre-trained models. So in order to do the training, you're going to require some two things for the model. First is the config file. Basically, what are the layers inside this architecture that you will build? And the second part is the pre-trained weights for that architecture. So for example, we come here. But do not download this. Yep. So here we see the what is it called? The config file. Inside the config file, we start with simply a couple of configurations for the training. So here we have the learning rate, number of steps. So this is max batches or number of epochs. The width and height of the image, number of channels, just some values for the optimizer and for the augmentations. And the rest is going to be, as we have seen before, so convolutions, some other convolutions, and lots of like routes between these convolutions. Here we see the activation function MISH. We will speak about it in more detail in the advanced computer vision course. And the most important part is the YOLO layer. So here we see, this is the YOLO layer. First, here you put the number of classes. This is very important. Second thing is every single convolutional layer that comes before a YOLO layer, we must change its number of filters. Now, for those of you who just still remember the lecture, can you tell me the final layer for final convolutional layer that comes before the classification and object detection must have how many channels, how many filters? Equals. We saw it in the lecture, we repeated it in many times.
5 plus number of classes multiplied by 3.
Perfect. 4 plus 1, which is 5, plus number of classes multiplied by 3. So if you're going to train a new architecture, you must, for a new data set, you must change this value, right? So this value depends on the number of classes that you have. Certainly, you're going to have much lesser classes than the original data set that they have trained on. So it's always nice to, or it's always important to change this number of filters that comes before every single YOLO layer. Basically, YOLO layer is the layer that will do the classification. So here you can see the anchors, for example. This is the number of classes and just some other information related to the object detection and classification. So this convolutional layer must be ready for the detection of the objects. And in order to make it ready, we must specify the correct values. Other than that, there's nothing else you should configure. The second part is the data. To train, basically, this one, first step is to create the model or to make the project or make darknet, basically. And then you specify, of course, the configs. Inside, another thing inside the configs is the following. Number of images per batch, number of subdivisions of each batch. So this is just to increase the use of your GPU. And this is kind of to relieve your GPU a little bit. This will allow you to add a bigger batch size to your training. Max batches is the number of epochs. Usually, a very good number that the researchers of YOLO before have set is number of classes times 2000. This is the number of epochs or the number of iterations. Sorry, not epochs, the number of iterations through the training data you will pass, right? So this is the number of batches you will sample from the data. This is just for the model to save different versions of itself, and usually you just specify it as 80 or 90% and 90% of the maximum batches. This will allow you to kind of fight against overfitting, let's say. And of course, this is for the height and width of the image. Again, this value should be the same value as the one you've used from the config. So if you want to use the same, what is it called? The same weights, pre-trained weights, try to use the same image sizes as they did in these in this pre-trained models. Usually you will find different versions for every combination of widths and heights. There are 3 combinations. So you will find all of them have their different config files and their different pre-trained values. And then of course, YOLO layer, we change its number of classes in every single YOLO layer, depending on what type of architecture, you might have 3 YOLO layers, you might have more, and you might have 2 YOLO layers. So this depends on the architecture of the YOLO before that you're using. And of course, do not forget to change filters equals according to this formula, right? So number of classes plus 4 plus 5 times 3 in every convolutional layer before each YOLO layer. But keep in mind only the last convolutional layer before each YOLO. So the others, keep them as they are in order to use the pre-trained weights of the neural network that you have just used. We do not use Gaussian layer in this course, but in the advanced course, we will speak about these. And then the second part, so this is about the model, configuring the model. Now the second part is to configure the data. And for that, we have 2 main files that we should configure. The first file is objects.names, very simple file that contains only the names of the classes. So for example, human being, dog, cat, stuff like that. And we have the second file, which is the object.data. The object.data is what will be sent for the training script. And it will tell the training script how many classes do we have, what are the training images, what are the validation images, where is the names file, object.names file, and basically where do you save the pre-trained or the trained models. So backup is the location where you will be saving the different versions of the trained algorithm. Now, I don't think we will have enough time to go through the structure of the data set, but simply, as you have already guessed, if you use RoboFlow, for example, you come to this data set, there are different versions that you can easily download. So for us, if we want to train, for example, scaled YOLO before, do the following. Nice. You copy this code, and then you come here to choose a model, say scaled YOLO before, go to this Colab version of scaled YOLO before. Should be quick. Yep. So only thing you will change is come here, replace this line with the line that you copied, and then just run all, right? Run all, and everything will be working very fine. So here, this is like a Colab notebook that will download, or just download YOLO, scaled YOLO before, install all the requirements, and then just download the data from RoboFlow. Here you will have the configs, and later on we will do the training of the YOLO before scaled. After it, you will do the, of course, evaluation, and all of that is done for you for free. If you want to, for example, play around with, let's say, YOLO v5 PyTorch implementation, continue, take the code, choose the model, YOLO v5, go to its notebook, only go to the location where the training, where the data is being loaded. Here it is. Replace this one with the link that you just got, run all, everything will be working. You will have your model already set up, and everything is done. So I will not be able to go through more detail about each one of these different scripts, but they're very easy to understand, very easy to use, and they're quite well described. Maybe another time we will go through the YOLO before architecture, especially about these arc values and the config files, the different config files. Just reading them does provide a lot of understanding of the models. So it's always quite useful to see it happening in action. But just remember, this is how the training is done. Again, we call the make or the made file of darknet using this detector train args, and we give it the object.data. The object.data sends or locates the number of classes, the object.names, and the location of the training data. We give it the config file for the YOLO before tiny, in this case, for example, and we give it the location of the pre-trained model. Don't show is just something that you should send if you are doing the training on some sort of server. So for example, in this case, we do not have a GPU to interact with the server of Colab. So you send don't show to specify not showing, basically just a window of the training happening. And MAP is just about calculating the mean average precision at different steps during the training part. Again, the final thing is just how do we use it for testing or for evaluating or for inference. Simply you call the same script, but now we do not call it with detector train. We're calling it as detect directly. Give it the config, give it the weights, and give it the image that you want to inference on, and he will give you the results in some sort of like here are the classes, here are the object, here are the those rectangles, bounding boxes, and of course we'll give you some sort of an image that already draws these things, and you will see the speed is very crazy, like it's very fast and very speedy. So thank you all for attending. Do you guys have any questions so far?
Do we need to know all these things about versions and other stuff?
You will get used to it, honestly. Just building throughout your project, you will get used to it. If you're going to build a project for this course for object detection, all of these different versions, you will get used to them. You will work with all of these scripts. You'll see it's pretty easy, and you will develop some sort of an intuition. This case, I will use this one. This case, I will use this one. Pretty easy.
And what about our theoretical midterm? when we will get our grades?
Yes, sorry, I did not upload your grades yet. I did already grade like at least the majority of you. The grades are good for what I've seen. There are some bad grades, but the majority are pretty good, right? I will upload them as soon as possible.
Okay, thank you.
Anybody else has any different questions? If there are no questions, then thank you guys so much for attending. I will upload the recording and the lecture for those who did not attend. Probably they're still sleeping. So for those who did not attend, you can still watch it on YouTube and on like the Moodle. And good luck with Karam for your lab. So see you guys on Tuesday, right? Yeah. See you.
Thank you. Goodbye.
Goodbye.
Thanks. Goodbye.
Thank you. Goodbye.
Thank you.